Welcome back everybody for another deep reinforcement learning tutorial. In today's video, you are going to learn how to implement n-step deep Q learning. I provided some starter code for you, so all you have to do is follow along. Let's get started. So the paper we are working off of is DeepMind's original paper on asynchronous methods for deep reinforcement learning. This is the paper that kickstarted A3C, and as far as I'm aware is the first really major paper where multi-threaded deep reinforcement learning was widely utilized. Now we've already done the A3C video, so I'm not going to go over all the code I did in that. Instead, I'm going to provide starter code for you in a GIST, and we're going to fill in the solution for the deep Q learning agent to flesh out the algorithm. The algorithm we're going to be implementing is right here in front of you in the paper. Now, a few things that you need to know is that this is going to be using PyTorch, so we're going to go over our installs, our versions in a moment, but make sure you have PyTorch installed, and I do recommend that you utilize your CPU instead of the GPU for this, since this is multi-threaded, unless you have a bunch of GPUs laying around. So the algorithm we're implementing is right here. The idea is we're going to run for some number of steps, say 20 steps, and that's going to be our time horizon. And then every 20 steps, we're going to compute these returns, and we're going to use those returns to calculate our gradients. Now, this algorithm, the way they originally did it, the end step is just the number of steps until the end of the episode. So for every single step, n varies. So we're always going to be taking the difference between each individual time step and the max Q, which is this quantity here, the max Q for the end of the episode. So n is not fixed, it is variable based on whatever time step you're looking at within that time horizon of steps. So this is going to be relatively straightforward. Let's head to our terminal and get started. So here, if you do a git clone on the GIST, I will link that in the description below. Of course, if you do a git clone on the GIST, you're going to end up with a whole bunch of different files. So I have the solution already provided for you. So if you want to run it, you can just change agent solution to agent.py, or excuse me, the reference to importing from agent.py to importing from agent solution, and it'll run right off the bat. But let's take a really quick look at how this is structured, because this is a multi-threaded program and it's a little bit different than you might be used to if you're not familiar with multi-threaded programming. So we have to handle multiprocessing, how we're going to handle starting of threads. We're going to have a global episode number. We have to pass in an environment we're going to be using, which is Pong no frame skip. We're going to do 8 threads. This is specific to my system. If you only have an 8-core CPU or an 8-thread CPU, lower this to something like 4. For this particular environment, we have 6 actions, and our input shape is going to be downsized from the default, I think 260, 320, something like that, down to 42 by 42. We're going to stack 4 different frames. Don't worry, all that code is provided. It is a lot of work. You don't have to worry about doing that. And then we're going to spool up our parallel environments. So let's just check that out next. And you can see that this is a class that instantiates some number of threads. A global agent shares the memory, shares our memory for our target and online networks, and has a global optimizer, and then does the operation of spooling up the individual processes as well as getting them to run. So our target is going to be worker, which is imported up here. So let's take a look at that. That's where all of the work really happens. So this is where we have our main loop for our program. All we have here is stuff to handle bookkeeping, like how many maximum steps, a local agent. So if you've seen my A3C video, you know that the way they originally handled it, which they have since changed, is to have each individual thread running its own local agent that then uploads its parameters to a global agent. Once it finishes the calculation of the gradients, then the global agent can calculate the gradients and then update its parameters and download that to each individual thread's agent. So it's a little bit convoluted. They changed things up slightly in later papers, but that's how we're going to be doing it. And so this function worker will be executed for every single thread. So every single thread is going to have its own local agent and a reference to the global agent. It's going to get its own environment, and it's going to be playing each individual episode on its own. And you can see here that we do all the normal stuff, like getting an observation, resetting our environment, remembering the stuff that's going on in the environment, and then every, in this case, 20 steps, we're going to sample our memory, calculate our loss, zero our gradients, backpropagate, clip our gradients. That's something that's very common in deep Q learning and various other algorithms. It's not strictly necessary. And then it's going to upload the local gradients to the global agent, step the optimizer, and then download the parameters from a global agent to each individual thread's agent, and then clear the memory and increment your episode counter by 1. And then we do have a global episode lock, so you can keep track of how many episodes have been played globally amongst all of the threads. And then we have some typical print and debug stuff here. Now, I like to uncomment this if name equals 1 because it's just a little bit easier to monitor the progress of one thread because you get more consistent performance, right? Each individual thread starts in its own little corner of parameter space, and so it's going to have different performance. And so if you just kind of print out the result from whatever finishes first, you're going to get performance from various different threads, which kind of doesn't pollute, but makes things a little bit more difficult to understand what's going on because you're getting performance from different threads. It's harder to know if it's actually learning. But nonetheless, I've set it up to run so that it'll print the first available thread when it finishes. And then we have other stuff like our memory file. This is very simple. It just handles the memory as a collection of lists and then dumps those memories back into the agent file when necessary, the main worker when necessary to pass them into the agent for learning. Then we have our shared atom. This code I took from somewhere else. I think in the A3C video I properly attributed that. Or maybe it was in the course on my A3C course, on the ICM course. But nonetheless, this isn't exactly my code. I've used it from somewhere else. But what it does is it handles sharing and optimizer across threads. And then we have our wrappers. Now, this is where we handle all of the Atari specific stuff, like repeating an action, pre-processing a frame, which is just downsizing it from the 84 by 84, I think the 240 by 360, something like that, to the 84 by 84 or 42 by 42, whatever size we want. And then a function to handle, a class to handle stacking the frames. And then we have our function to make each individual environment. Okay, so that is it for, I think, all of the stuff that we really handled in the A3C video, so check that out if you haven't already. But now we're ready to check out our agent.py file and start writing our DQN agent. Now here I have the basic class outline, where we're going to have our agents. We have functionality to choose an action, decrement our epsilon, update target network, calculate our returns, and calculate our costs. And I filled in the parameters that you're going to need to make your life a little bit easier. One other thing we didn't do is take a look at the network. It's just a garden variety convolutional neural network that dumps into a fully connected neural network to handle the action selection based upon the Q values for a given set of states. Pretty straightforward stuff. Let's go ahead and write our agent. So the first thing we want to do is create our networks. So Q online equals Atari deep Q network. That takes input dims and actions. And then we're going to have a Q target. It'd be helpful if I could type correctly rather than having typos already. Deep Q network, input dims and actions. Then we have our variables like gamma. We have our epsilon decrement, our epsilon min, our number of actions. That's for performing random action selection. And then we have our learn step counter and our update interval. And that's interval. And that is for how often we want to copy over our target network to our, our online network to our target network. Let's get rid of that extra line there. Then we have our choose action function. The first thing we want to do is calculate a random number. np_random.random less than self.epsilon. I think in my solution I have less than or equal to. Then we'll say action equals np_random choice number of actions. So what this does is In deep Q learning, we are using something called epsilon greedy action selection. So we have some hyperparameter of our agent called epsilon that determines the fraction of the amount of time that we take a random action to explore our environment. Because remember, our agent starts out not knowing anything about the environment, and so it has to do stuff at random to figure out how its actions affect that environment. And you do that such that over time you learn what actions are profitable and you can act greedily later on. So next we'll handle the greedy action selection. So we say otherwise our state is a tensor and the d type is t.float. We don't have to worry about the device here because everything lives on the CPU. Q equals self.q online states. We're going to propagate that state through our online network and use the argmax to find the most profitable action according to our current model of the environment. So we want to move that to the CPU. That's not actually necessary because everything lives on the CPU. I just have it to be pedantic. Now that I'm looking at it, I realize it's not exactly necessary. And we take the 0th element because the argmax returns the actual index and value of the maximum element of a tensor. And then we handle decrementing epsilon, which we can do next. Oh, of course we have to return our action. We don't want to forget that, otherwise nothing will work properly. Okay, next we handle decrementing epsilon. That's pretty straightforward. So we'll say self.epsilon equals epsilon minus epsilon decrement if self.epsilon is greater than epsilon min, otherwise else self.epsilon min. So it's going to subtract off epsilon decrement at every time step until it reaches the minimum value, when it's going to, at which point it'll just hover there. See, did I make any mistakes yet? Not yet. Next, we need our function to update our target network. So if our learn step counter modulus update interval is 0, in other words, if it's time to update our network, then we will do so. So what we'll say is source equals q online dot parameters the destination q target dot parameters, and then we say for param target in zip source and destination target dot data dot copy underscore param dot data. And what that does is it iterates over the zipped up parameters of your online and target networks and copies the data from the source, which is our online network, to the target, which is our our target network. So pretty straightforward. And these two lines here are just so that this next line here isn't too long, is all that is, just to make the code a little bit more readable. It's not necessary to break it up that way. I just did it for aesthetic purposes. Next, we come to the actual kind of meat of the algorithm, which is calculating our returns and our costs. So this is where all the stuff from the paper comes into play. So we're going to say q equals self.q target states. So we need to get that max q. We're going to say max action equals t.argmax. And remember, again, as I said in the introduction, we are taking the n to depend on the time step in our episodes. So we're always going to be taking the last state from our horizon, and so we want q sub minus 1, so the last value of q for that particular horizon. And dim equals minus 1. And we say if the length of q dot size equals 2, this is a batch of states, so we have a couple edge cases or a couple things we can deal with here. So it's entirely possible that the agent takes 20 steps and then doesn't finish the episode, and so it kicks back to the calculate R function with capital T 20 steps of data. Or it's possible that it took a single step and finished the episode, where, say, step 21, after processing a batch of 20 states, step 21 is the end of the episode, so you have a single state. So we have to take into account both possibilities, either a batch of states or a single state. And I do that by taking a look at the length of the q.size parameter. And then we say max q equals q sub minus 1 max a. Otherwise, length of q.size equals 1, say a single state, then max q equals q max action. Then we say r equals max q times 1 minus int of done. And the reason we have that 1 minus int of done is because that the q value for the terminal state is always 0 because no future actions, no future rewards follow. It's just a definition. Now we can calculate our batch returns. We'll say batch return equals an empty list. And so we're going to iterate backwards over the horizon. So we're going to say for reward in rewards, and we're going to reverse the list, -1 r equals reward plus self.gamma times r, batch return dot append r. And what this will do is it will accumulate the rewards, the returns over the course of the episode. And then we say batch return dot reverse because it's in reverse. We want to get it in the proper temporal order. And then say batch return t.tensor batch return dtype equals t.float, and then return batch return. And that is all we have to do for calculating our batch return. Next, we have to handle calculating our cost, which is actually pretty straightforward. Let's get rid of these extra lines. Okay. Now we can calculate our costs. So we'll say self.update target network. I like to do it at the very top of the calculate cost function. You can do it at other points in time. I don't think it's really all that critical. So we want to say states equals t.tensor for states, dtype equals t.float, and then returns self.calc return. We want to pass it in done, rewards, and states. We need our next q value, t.0 is 1, self.end actions, if done, else q online, tensor new state, t.float. So what we're doing here is saying that if the last time step we took resulted in a terminal state, we want the q value for that resulting state, the observation underscore in our main loop, to be a 0. Otherwise, we want to get that value from our online network. And then we'll say q equals self.q online states, q equal t.cat, q next q.detach. So we're going to concatenate all of our values for our states and the next q value. And we'll say rewards tensor rewards indices equals t.tensor, MPA range len of q up to the last element. Make sure we close out our parentheses properly. Say q values, q sub indices, and actions. So we want the actual values. We want the q values for the actual actions we took. So for the current estimate of whatever those q values are, for each of those states, get the value for whatever action the agent actually took. And then q values sub done equals 0.0. So again, if we have a terminal state, the value is 0. And then total loss equals, 1/2 times returns minus q values quantity squared. So the mean squared error. Total loss equals total loss dot mean. That's where we handle the mean part. And then we say self.learn step counter plus equals 1 and return total loss. Okay, so we don't have any obvious typos. This is the very basic setup for an n-step deep Q learning agent where the n is set to the end of the episode. So it's a variable based on whatever time step in the batch you're processing is. In a more generalized approach to this, you would fix n at something like, say, 5 steps, and you would have up here, instead of this -1, you would have q sub current step plus n. So you would have to take into account what to do when you are, say, 4 steps from the end of your horizon, 3 steps, 2 steps, in which case you'd probably just use the last state anyway. But nonetheless, I'm implementing it to be faithful to the paper, but letting you guys know how you would modify this for a more general end, which is what they do later on in subsequent papers. So let's write quit, and we should be able to run this by typing python main.py, and this is famous last words kind of stuff. No, it does run straight away, and you can see that it doesn't print out at regular intervals. It prints out as soon as one of the threads finishes. And so what this will do is it is going to kind of oscillate over time. It's not the most consistent performance because we're not monitoring a single thread. Actually, I think, let me take a look. Let's take a look at the worker. I am going to change that because I do like it better that way. So, and in the gist, I've already uploaded the gist for this, so it is set up the way you see it here, where that if name equals 1 is commented out. So of course we have to indent those lines, and then we can run it again, and it'll give you a little bit more consistent performance, as well as output stuff at a more consistent interval. So, oh, but it's still printing out. Good grief. So take a look here. What it's doing is it's printing out the global episodes. So thread number 1 finished on episode 5, so 4 other threads finished before it, and then 5 or 6 other threads finished before it could finish another episode. So you can see that it is in fact asynchronous. Let's just change that. So instead of global idx.value, let's print out episode. So that way you get the episode for thread number 1. And then you'll see that it's just, oh, that's interesting. No module found multiprocessing. Very strange. I have never actually seen that error. Now that I'm looking at it, it's very weird, because that's in the Python 3.7 init.py. That's not in, it doesn't look like it's anything that I'm doing. Interesting. I honestly don't know, because I've never seen that error before. That's the first time that's popped up. Of course it does it on a video, so you guys get to see it live. Very strange. I'll monitor that. I'll play around with this. This didn't do it in my, at least I didn't see it pop up in my solution when I originally coded this. Very strange. But nonetheless, you can see that now it is printing out the output from a single thread instead of whichever thread happens to finish first, or whatever global episode it was on when thread number 1 finished an episode. And you can see we've already made about 20,000 steps because we're dividing by 1,000,000, and it's doing quite poorly as we would expect. So I'm going to let this run for a little while, and we're going to come back and verify that it's learning to make sure I didn't make any silly mistakes. Alright, so this has run for a little while, and you can see that the average score is going down and down and down. And we're seeing individual episodic scores, 17, I saw a 15 up here, 15, a 17, another 17. It is oscillating around a little bit. That is pretty typical with this algorithm, but I'm confident to say it is learning. So we didn't make a mistake in our agent class, so that is deep Q learning with end step returns for you guys. So check out the gist for this. It's going to be necessary for you to run the code. I didn't want to go over all of the frame stacking and all of the stuff I've already done in the channel before, because it's really not pertinent. It kind of is a bit of a waste of time, especially when I've already done it in a video. You guys can just watch that, which I highly recommend. Now, just to demonstrate to you where I got that, I didn't make up the claim of them using the final step of the episode. Let me show you that in the paper so you guys can see it with your own eyes. So here in the paper you can see it says each end step update uses the longest possible end step return, resulting in a 1-step update for the last state, a 2-step update for the second last state, and so on, for a total of up to T max, which is our capital T equals 20 updates. So that's where I got that from. That's from this particular paper. I'm not making that up, not trying to make things easy, just because I want things to be easy. That's how they actually did it. So there is the end step, asynchronous end step Q learning algorithm. If you didn't find stuff clear in this video, I would invite you to check out the A3C video to get a little bit of a broader update on how we wrote all that code with the worker thread and all that kind of stuff. But from the perspective of just end-step Q learning, here you have it in this particular episode. So if that was helpful for you, make sure to hit the like button. It does help with discoverability because I'm terrible at making thumbnails. I'm a programmer, not a graphic designer. So hit that thumbs up, drop a comment down below for the algorithm. Make sure to subscribe, and I'll see you in the next video.